All right. Okay, people. So today we're going to be going over the AP Physics Study Guide questions. And they are pretty simple this time around. They're for quiz 6A. I'm going to put them up here just for my reference. And here we go. So this is AP Physics, Unit 6, Simple Harmonic Motion, the first quiz. So let's go through all the questions. And you can follow along if you want. But we're just going to start with number 1. A pendulum of length L having a mass of m oscillates with an amplitude of a on the surface of the Earth. Where is the pendulum's maximum acceleration? All right, so this one's pretty simple. So we're going to we actually don't even need a calculator for the first two. So we're going to go right here and right there to create some functions. So we already know that our position function looks like a sine wave. And if you've taken calculus, you know that the derivative is the rate of change, right? So rate of change of a position is by definition velocity. So when this position starts up really high and comes really low, when the slope is 0, that's when we get our intersections with the x-axis. And that'll happen here too. So we can note that this is the steepest right here, and it's negative, so it's going to look something like this, and it's the steepest here positively. So this is v of t. This is going to be s of t. S is used for position. And then for this one, we're going to do a of t, which is acceleration. And what's the rate of change of velocity? Acceleration. So if you use the same principle, where the slope is 0, we're going to have our zeros. When the slope is 0, we're going to have our zeros. And when the slope is highest is right here in the middle. And that's when the maximum acceleration occurs. And you'll notice if we line it up, it's at an endpoint. It's when it's furthest away from the center. So the answer should be B. It's at A. When x is equal to A, because A is the amplitude, that is when we'll have our maximum acceleration. All right. Moving on to question 2, we actually don't have to erase any of this because it's asking us for maximum velocity now. And this one is pretty intuitive. Maximum velocity should occur at the equilibrium point, but we can also prove it with these graphs. So the equilibrium point is at x equals 0. And these are all on the t-axis, by the way. These are all a function of time. So we'll have x equals 0 here. And we know the velocity is a maximum when it's the furthest away from 0. So this is going to be 0 velocity in the middle, and this is going to be 0 acceleration in the middle. I should probably draw out this graph. So if we have it like this, and this is positive, it's going to look like this. So it's exactly the first one, but flipped. And this makes sense if you know calculus, because cosine of x, if you take the derivative, is equal to negative sine x. And then if you take the derivative of that, so we have d dx negative sine x, we get negative cosine x. So if this is our velocity, this is our position function, which is going to be p, we'll put p. And if this is our velocity function, which is v, this makes sense that this is a. So these are exact opposites of each other. But that's a side tangent. But that should be pretty obvious to you if you've taken calculus. But other than that, moving on. So for number 2, that means the maximum velocity is at a equilibrium point, because it's right here, and these are at zeros. Okay, so number 3, a pendulum of length L having a mass of m oscillates to a maximum angle of 7 degrees. Where is the pendulum's maximum displacement of x? So this is pretty obvious. The answer options sort of give it away. If you're at 7 degrees and this is equilibrium, obviously it's when you're at 7 degrees, that's the biggest. So I'm also going to write out the answers here. So 1 is going to be B, 2 is going to be A, and 3 is going to be B, obviously here. All right, moving on. We have 4, 2 equal length pendulums, one of mass m and one of mass 2m oscillate on Earth's surface. mass m reaches its amplitude at 5 degrees, and mass 2m reaches its amplitude at 10 degrees. Which mass is more likely to exhibit the greater period of t? So if we can finally erase these, we don't need these anymore. Okay, so we're given, if you remember from the lesson, t is equal to 2 pi times what? L over g, right? Because think about it, if gravity pulls down harder, if gravity pulls down more on the thing, it should oscillate faster, so the period's smaller. But if the string is like here, it's going to oscillate much faster than if it was all the way down here, right? Because there's more torque needed. But that's a topic for another time. But anyway, if t is given by the length, it depends on the length and the gravitational constant, then none of the options besides d will work because they all involve changing something about its amplitude or something about its mass, which doesn't matter. So it's correct that D should be the right answer, that neither will exhibit the greater t because t of 2m is equal to t of m, which is true because this is not based on mass or amplitude at all. All right, so for number five, a mass is attached to an ideal spring, which is one that obeys Hooke's law. So remember, Hooke's law is force restoring is equal to negative kx, like that. Oscillates horizontally on a frictionless surface on the Earth. The spring stretches and compresses with equal but opposite amounts of force. So that means on opposite sides, it's going to compress with the same force if you took the magnitude, which are the factors that affect the period of the oscillator. All right, so this happens to be of a spring, so it's different from the pendulum one, but it's of a very similar concept. It's still going to be 2 pi, but instead it's going to be spring constant on the bottom, and then it's going to be the mass of the oscillating object. So, if you're looking at this, well, it's pretty obvious what affects it, right? The t is dependent on the mass and the spring constant. So 5 is going to be mass of oscillator, and then it's also going to be spring constant k. All right, now moving on to the back side. These ones I actually haven't done, so we'll work through them together. It's all right. That's the beauty of physics. You got to work through all the problems. And that should work. Okay, a mass of 2 kilograms is attached to an ideal spring, so once again, one that obeys Hooke's law, with a spring constant of k equals 25. Okay, so let's write out our work here, 6, and I'll just keep the answers running over here. 6. We know that it has a spring constant of 25 newtons per meter. K equals 25 newtons over meters. And we know it oscillates on a horizontal frictionless surface on the diagram above. So you can't see the diagram above, obviously, because it's too small, but I'll draw it for you guys. So it's going to look like this. And then this is the wall. And then we're going to have x minimum, x zero, x maximum. And let's just say our object is here. It has 2 kilograms of mass. I'm actually not going to draw it in there. That's too small. And then we have x equals 0 here. And then we have negative 1 meter, positive 1 meter. This is how our thing is set up. This is the maximum over here. This is the minimum. And then obviously there's that spring. And then there's no friction at all, so we don't need to worry about any of those equations, which is really nice. And now it's going to ask us, the spring stretches and compresses with equal but opposite amounts of force. If the oscillator has an amplitude of a, which is 1 meter, what is the magnitude of the maximum acceleration? All right, so the force of restoring force is always equal to negative kx. But if we want to know that this force, this spring, is applying a force on the oscillator, we know that it's also equal to the mass times the acceleration. So if we want to find the maximum acceleration, then we need to find where is it a maximum. And if you remember from the first side, using our 3 derivatives, the S of t, v of t, a of t, you can remember that the maximum acceleration is at the very ends, which is 1 meter. So we're going to get that x equals 1 meter, or a is actually equal to 1 meter. So a is equal to 1 meter. So negative ka is now equal to mass a. So a is equal to, well, it also wants us to find the magnitude of the maximum acceleration. So these should have absolute value bars, which is my bad, like this. So from here, we're going to have m over k, like this, absolute value. And this is pretty easy. Oh, shoot, my bad. This is not m over k, it's k over m. Brain fart. All right, like this. And this is equal to 25 over 2. And it's going to be Newton meters over, it's Newton meters times meters, because it's 1 meter, over kg, which is, in fact, meters per second squared. So the units do cancel out very nicely. So you get 12.5 meters per second squared, and then maximum acceleration. So get that down while I write it over here. All right. So if that's done, I'm going to be erasing the board. And we'll move on to the second one, the next one on this page, which is question 7. A pendulum of length L. So we know this. I'm also going to draw this one for you guys too, because the diagram is much too small. Okay, that wavy line is supposed to represent the equilibrium. And so since it's at 11 degrees, sorry, I took a phone call. I'm going to write that now. It's at 11 degrees. And then this will be the actual maximum amplitude right there. So it's saying it oscillates at a maximum angle of A. What is the magnitude of the pendulum's maximum restorative force? So the maximum restorative force is going to depend, remember, as the pendulum follows simple harmonic motion, force is dependent on displacement. So obviously the greatest force is going to happen when it's the furthest away. So the force is equal, if you remember, the restoring force is equal to mg sine theta. So if we want to know what the maximum restorative force is going to be, well, you just take the mass, which is 1 kg, and then we need to find g. Well, actually, we know what g is. It's 9.8. So we have 9.8 times sine of 11 degrees, and that's going to give us our maximum restoring force. And if I just use the calculator here, we have 9.8 times sine 11. This gives me 1.870 if you round to the right amount of six figs newtons. So that's going to be number 7. And it's not in seconds, apologies, it's just newtons. So that's the maximum restorative force. All right. Let's go to number 8, which is, what is the magnitude of the maximum acceleration of the pendulum described in question 7 above? So let's just go with 8 right under it. What is the maximum acceleration? Well, remember, I mentioned the maximum good point. Maximum acceleration, A max, occurs at x equals a. Therefore, F max occurs at x equals a because F is equal to ma, remember? So that's a good thing to know, right? Okay, so we can find our maximum acceleration from the formula F equals ma, and we know that F is equal to 1.870 divided by the mass, which is going to be 1, is equal to a. So that means a is equal to 1.870 meters per second squared. Pretty nice. Okay, now for 9, what is the period t of the pendulum described above in question 7? So let's just keep going down, and then we have a 9 here. Remember, t is given to be equal to 2 pi times square root of length, which is going to be length equals 0.4 meters, 0.4, over g, which is 9.8 meters per second squared. So that means t is going to be equal, just plug that into your calculator, quite simple, 0.4 over 9.8, and this gives us 1.2694 seconds. So 1.2694 seconds. And then 10. What is the resulting period t if the length of the pendulum above is decreased to half its original length? Well, this is pretty easy. Just divide this 0.4 by 2. So this is going to give t is equal to 2 pi 0.4 times 9.8. And remember, if you divide by a 2 on the inside, it's under the square root. So is it really dividing by 2? Remember that. It's not. So if we're dividing it, we're going to get 2 over 7 pi, which is equal to 0.8976. So if you divided by 2 and you expected it to decrease by half, did it decrease by more or less than half? Let's see. Well, that looks like it decreased by less than half. So why is that? And that's because it's under the square root. So just keep that in mind. Sometimes it seems intuitive, but really it's not. And then once again, this is in seconds as well. So this is going to be 0.8976 seconds. And that is all the questions that are on this study guide. So I hope that was of help to you. And if you liked it, please drop a like. And if you have any more questions, just shoot me a question and I'll try to answer it as best as possible. All right, thank you.